presentation is it's a 30-minute slot for the first one, so we'll have 28 minutes for the presentation itself, and then we have a few minutes for Q&A. If you have some specific questions and you don't want to ask them yourself, you can put them into chat and I can read them afterwards, depending on the time we have. So please, the first presenter, the floor is yours. Okay, I don't know about the others. I can't hear anything.
Okay, can you hear me now? Can you hear me now?
Yes. Please. Great.
Sorry, it's this just like. Yes, you can hear me now, right? There is sound. Where is my sound? Yes, there is sound. Okay, great. So shall I start now or?
Yes, please. Yes.
Okay, great. Okay, so my name is Viktor Yakovenko. Okay, and so this talk will be about economic inequality from statistical physics point of view. So it's an overview of the work that I have been doing for the last 20 years, starting from the first paper published in 2000 up to the most recent paper published like last year or so. Because time is limited, I will only cover two topics. First, I start with statistical mechanics of money, and then I will discuss the actual data on income distribution. I have to skip the other two topics. Okay, so let me start quickly with a quick historical note. I mean, historical pictures. So this is the Ludwig Boltzmann, one of the founders of statistical physics. And for those who know statistical physics, his name is associated with this Boltzmann-Gibbs probability distribution, exponential distribution for energy in a system in thermal equilibrium. I will go very quickly because time is short. Another name is Wilfredo Pareto, who is well-known economist and sociologist, and what is associated with his name is a power law. So power law distribution of income, wealth, and this kind of thing. So so these two simplest mathematical functions, exponential and power law, will appear recurrently in my talk. So I wanted to introduce these portraits right away. So let me start with the first topic, which is this analogy between distribution of money and energy in statistical physics, the starting point. So first, very briefly, let's consider some kind of gas of atoms and consider collisions between atoms. So they collide, so they come with those energies, and they collide like billiard balls, and some energy delta epsilon get transferred from one atom to another. Okay, and so energy get redistributed in collisions. Of course, total energy is conserved. The sum of the initial and final is the same. And then the question is, after many collisions, system will come to some kind of thermal equilibrium. And what is the probability distribution of energy in equilibrium state? And it is given by Boltzmann-Gibbs formula, and it is exponential distribution, exponential decreasing function of energy epsilon. And the parameter temperature is basically the average energy per particle. Sorry, I have to skip the derivation because time is short, but those who know statistical physics are surely familiar. Otherwise, it is a standard textbook stuff. It can be written in different ways by using, say, detailed balance equation or by maximization of entropy, subject to constraint. Anyway, so this is a brief kind of summary of statistical physics. Now let's move try to go to the economics. So let's replace the story. Let's now consider an ensemble of economic agents. Okay, so people say in this chat room, this Zoom room, okay, so they engage in some transactions. I mean, they produce something. They say let's say I buy a bottle of water from Ladislav, for example. So he gives me a bottle of water. I give him $5. Then I drink the water, but we'll never see each other again. But his money balance is $5 up. So these agents have money balances, M1, M2, and after the in transaction, some money delta M is transferred in payment for goods and services. So after the transaction, one agent has higher balance, another one lower balance. So this transfer of money in economic transactions looks somewhat similar to transfer of energy in collisions between molecules in a gas. And so, for example, this local conservation law, meaning the sum of money before and after transaction is the same. Me and Ladislav, our money balances are exactly the same after I transferred him $5, right? So anyway, so the question is, after many transactions, what would be the equilibrium probability distribution of money in the system? And one can make a conjecture that it may be similar to Boltzmann-Gibbs exponential distribution. It's not a rigorous statement, it's a kind of a conjecture. But let me show you now some computer simulation to illustrate this point. We have a big number of agents, okay, and initially we give each agent money balance, say $10, for example. Okay, so initially we prepare the system in a state which is perfect state of perfect equality. Everybody has the same initial money balance. So the distribution of money then is represented by this histogram, which is a delta function. Okay, and then we'll run a simulation where we randomly pick a pair of agents and transfer some money. To keep it simple, it will be transfer of $1, and then pick another pair of agent, transfer another dollar, etc. So we just, it's a very simplistic, very stylized kind of model to, to simulate movement of money in the system, in the economy. Let's see what happens in this system as we start to run it. Okay, you see, it starts, this delta function distribution immediately starts to broaden. So it looks like diffusion. It's Gaussian kind of shape. It's like diffusion of in a money space. So just by random transactions, some agents end up with higher money balance, and some agents end up with lower money balance. Of course, the total is conserved because it's a closed system. So basically what you see is some kind of inequality develops in the system. So the fact that some people have more, some people have less, means that already some inequality develops in the system. So we observe that the state of perfect equality, the initial state, is totally unstable. Once you start making any transactions, some sort of inequality will start to develop in the system. Now, if I continue running a simulation, let's see what happens. Simulation, the distribution becomes asymmetric because I put a boundary condition at 0. So I actually do not allow money balance to go below 0. That means if I spend all of my money, I cannot buy anything anymore, but I can receive money, I can work for somebody, get paid, etc. So agents do not disappear, but if there is 0 balance, they just stay there until they receive some money, but cannot spend money anymore. So in this way, this is basically hard boundary condition imposed at 0. It's a little bit like ground state energy for gases, for kinetic energy. And in simulation, it is enforced in this way. If you pick a pair of agents and one agent has no money to pay, we skip this transaction, go to the next pair of agents. So basically, because there is boundary here and no boundary there, the distribution becomes asymmetric. Okay, this probability density starts to accumulate near the boundary. And if you keep running the simulation and wait long enough, eventually it approaches this red curve, which is exponential with a graph of exponential function. And then it stabilizes there. So, after a long time, after many transactions, so the probability distribution stabilizes at exponential shape. Transactions continue, agents continue to transfer money, but we reach the statistical equilibrium, the probability distribution of statistical equilibrium, which is given by exponential function, Boltzmann-Gibbs, as I discussed before. If I put on horizontal axis energy, I would be, lecturing on physics. Now, if I put money, it becomes economics. And so this distribution is very stable because it also, let me just stop the simulation. Okay, because it also maximizes entropy. The graph at the bottom is entropy as a function of time. The initial distribution had 0 entropy because it has multiplicity 1. It can be prepared in only one possible way. But this exponential distribution, as it was proven by Boltzmann, has actually maximal entropy, and you see the entropy spontaneously increases until it saturates at the maximal value. So from physicists' point of view, and of course this distribution looks a little bit like real life, meaning there are few agents which are rich, whose money balance is high, a few rich agents, and many poor agents, right? So it is qualitatively similar to real life. And so I would, as a physicist, I would call this exponential distribution representing the natural inequality. Natural, I mean inequality that develops simply because of randomness, because of probabilities, because keep in mind, all these agents, they do not have any attributes, meaning they do not have skills, education, etc. And also, this is what I would call equal opportunity society, because every agent has equal probability to be picked up for any transaction, to get money, receive money. There is no bias, discrimination, preferences, whatever. But of course, as you understand, equal opportunities doesn't mean equal outcomes. This is like a lottery. Everybody has equal opportunity, equal probability to win a lottery, but not everyone.
I'm sorry, there seems to be some problem with your sound. It's like robotic. So I'm not sure what's going on.
I don't know what's actually going on, but this is it.
Yeah, I don't think anyone can hear. I don't understand a word, to be honest. I don't know about anyone else. We just agree that it sounds cool in the chat, but it's quite difficult to understand anything. Maybe if you can try to unplug the sound and plug it back or something.
Okay, how about now?
Yeah. Now it's fine. Perfect.
Okay, yeah. The problem could have been is that this video, animation video, could have interfered with, too much data maybe. But I'm done with animation. So is it now good? Sound good? Good. Okay.
Yes.
So no more computer animation. So that maybe was taking too much bandwidth. Okay. So anyway, if you didn't hear that at the end of my previous slide, basically I'm switching to the second part of the talk, which is data-based. The first part was kind of motivation illustration. I hope you get the idea, right, about this simulation, right? Okay. So that gives the idea. Now let's switch to the data. Well, it turns out it's very difficult to find data on a probability distribution of money balances. Yeah, but there is plenty of data available on distribution of income. Okay, so because this is collected by various government agencies, it's publicly available, etc. So then we just decided to analyze income distribution as opposed to money balance distribution. If you can think of the second part as just empirical data analysis. First, what we did, we went to Bureau of Census, United States Bureau of Census, and downloaded data. It is available. Downloaded raw data and made a histogram of income distribution. So on horizontal axis, we have annual income in thousands of dollars up to $120,000. So we divided this into bins, counted how many people have income, report their income in different bins, and we had the histogram. So this is a histogram of income distribution data. And then, being inspired by the first talk, or for the first part of the talk, we tried to fit it to the exponential function. So this is a fit to exponential function. And you see it's a quite good fit of the data. There is some deviation at the low end, but this is very low income. This is below $5,000 a year. So, there would be, one would expect some problems near the boundary. Anyway, it's even better to see this exponential distribution if you take a logarithm. And so then it becomes a straight line. So this is the same data plotted in log linear scale. This is logarithm of probability. This is annual income. And see the data basically fall on a straight line, which basically, well, confirms exponential distribution. It shows that was subject to our second paper, evidence for exponential distribution of income in the United States. So it turns out distribution of income is indeed exponential. And this was totally unknown to the economists, okay? They would think log normal or something else, but in fact, it is exponential. However, this data does not sample very high end. Census data is a sample, survey of population is a sample of population. So it does not cover very high incomes. So to see what happens at the very high incomes, one more thing before I go there, we fit to this straight line in log linear scale, and the slope of this curve, of this line, determines the parameter temperature, which is what we call income temperature. It is simply the average income, and it determines the slope of this. It's a dimensional parameter in this formula. Okay, so anyway, because I will use it later. So anyway, so what we did, we went to a different data source, and this is Internal Revenue Sources, the American tax agency. And this data is also publicly available. And they have huge data set. I mean, they have 100 million tax returns every year. And so now we show cumulative probability distribution on this graph. On the horizontal axis, we show again income, adjusted gross income. That's income according to IRS definition. And the inset is in log linear scale. So this is a cumulative probability in logarithmic scale. And horizontal axis is income in linear scale. And you see the data points fall on a straight line. So again, this totally different data set from different agencies also confirms that exponential income distribution is exponential. However, the main panel is data is shown in log scale. So income is now shown in logarithmic scale that goes up to $1 million per year. And you see the upper tail of the distribution falls in a straight line in log coordinates, which represents power law. So in fact, if you look at this graph, well, we'll conclude that what it represents is a two-class society. And by two-class, I mean the following. The lower part of the distribution follows exponential law, and I associate it with the name of Boltzmann-Gibbs. And the upper part of the distribution follows power law, which I associate with the name of Pareto. And the whole distribution consists of two classes, which of course, surely there is a notion of social classes, and I'm certainly familiar with that, well, being educated in Soviet Union. But Karl Marx Capital was required reading in my undergraduate studies. Okay, but the point is here, we see just from the point of view data analysis, you just analyze, just make a graph of publicly available data. And here you see the two classes. It fitted with the simplest possible mathematical functions, exponential and power law. Now, as we did this decomposition, we can take the intersection point as some kind of operational boundary between the two classes. So we can read off certain parameters. Like, for example, how many people are in the upper class? Well, we go here. It is cumulative distribution, logarithmic scale. So it is 1, 2, 3%. So the upper class consists of about 3% of population. Number changes over time. I will show you the data. Whereas the lower class is the great majority of population, 97%. So this is the 99% you maybe heard about. Well, it turns out to be 97%, but that's minor detail. The point is there is databases for this distinction between two classes. Okay, this, by the way, are also known in some branches of physics, like astrophysics, plasma physics. They are known. The lower part is called thermal, and the upper part, the tail, is called superthermal. In some high energy physics, if you like, cosmic rays or whatever. But this was data for one particular year. Now, what about different years? So then we analyzed the data for 30 years. And the way we did it is the following. Of course, the average income, that is the temperature, it changes over time. So for each year, we did this exercise, did the log linear graph, extracted the slope of this curve. And from the slope, we extract the average income, the temperature, and then we normalize to income temperature in any given year. The average income actually increased by factor 2.5 over the last 30 years. So this is basic inflation. But what we do, we normalize to it. So now this is data for like 30 years. It's a very busy graph, but on the horizontal axis, we show rescaled income normalized to this average income, to the income temperature. So 1 means 1 average income, 2, 3, 5 times the average income. The data is split into this years and this year just for the purpose of visualization. It's not really important. It just the graph is too busy because there are so many years here. But the point is, data points collapse on the same lines. So the inset is log linear, and so basically data fall on a straight line. And so the lower part of the distribution doesn't indeed correspond to exponential distribution. The upper part, this is the power law tail. It is more dynamical. It changes significantly, especially for this range of years. It changes significantly. So the upper tail is dynamical. So the point is, we can do this decomposition for many years, and then we extract parameters of this decomposition. And now let me show you historical evolution of historical data about these parameters, specifically about the evolution of inequality. Let me skip this slide because time is short. Let me go to this graph. So this is evolution evolution of the fit parameters in these years. It's a very busy graph, but let me start with one parameter, which I think the most important, most representative, is F. It's a fraction of income that goes to the upper tail. You see, there are two classes. So some income goes to the lower class, some goes to the upper class, right? And so it's an interesting question, what fraction of total income in the system goes to the upper class? It can be actually easily calculated by this formula. Here, the average R is average income in the whole system, everybody, all classes, minus temperature, because temperature is average income in the lower class. So the difference obviously goes to the upper class. So the graph is shown here. This is the graph. These are years, from 83 to 2015 or so, and the scale is on the left axis. So what you observe is that this share of income going to the upper class was relatively flat, about 10% from 85 to 95. Well, relatively constant. But then it started to increase very rapidly, basically doubling to almost 20%. So what was going on? The dot-com bubble in stock market. Then stock market crashed, and so the share of upper class shrunk. But then housing bubble, subprime mortgage bubble started, and share of upper class increase exceeded 20%. Then this bubble crashed. And then what happened is, maybe I show this graph. So what we see the evidence that of income inequality peaks during speculative bubbles in financial markets. And then, of course, there is now a third growth. What is that? I think that's my speculation. I think what they call quantitative easing bubble. That is because the central bank, Federal Reserve, to overcome the great recession, whatever, of 2008, the central bank started to print money and inject huge amount of money in the system. They basically quadrupled their balance sheet. It was below $1 trillion. Now it is more than $4 trillion. So huge amount of money was injected in the system. But you see, because it's by central bank. But you see, central bank cannot deal with, well, banks. And so this money primarily went to banks, right? Then means to bankers, that means to upper class. So there is significant consequence for this significant growth of income inequality during the time of, well, economic stimulus, by central bank. Anyway, there are many more parameters on this graph. Time is running short. Maybe what I should mention is the following. If I maybe actually mention this graph, this is a Gini coefficient, that's a standard parameter that economists use to characterize inequality. What I can say is there is a formula that I can derive during using this decomposition into two classes. I can derive a formula representing Gini coefficient in terms of fraction of income going to the upper class, and all the inequality dynamics is perfectly fit, can be perfectly fitted by decomposition between, basically by relative share of income between upper and lower class. So in other words, the driver of inequality is really a share of the upper class with a share of the lower class. Maybe another observation is the percentage of people in the upper tail. It has been actually steadily increasing. Scale is here. It used to be only 1% of a population was in the upper class, but then it has been increasing to up about 5 or 6%. So that's another interesting observation. Now there's maybe 6 times more. It increased by a factor of 6. The percentage of people in the upper class. I don't know exactly what is the reason, but my speculation is because of this computer, connected economy, non-local computer connected economy. So anyway, I can talk more about this, but time is running short. So let me show maybe last 2 graphs of my talk. It's about other countries. So this was for United States, very extensive analysis. But recently, our most recent paper, this one, we analyzed income distribution in 67 countries around the world, just to see what goes on in other countries. So let me start, let me skip this abstract, but let me start with the data for the United Kingdom. And one more slide and I will finish. So here we show just cumulative probability distribution as a function of normalized income. Again, it's income normalized to income temperature for many different years, for many years. And this is actually basically pretty much linear slope in log linear scale, meaning distribution is exponential. Of course, you can see deviations at the high end. This is signatures of the upper class, upper tail. But now to make it even better, we can truncate the distribution, just drop few percent of data points in the top, so we can only leave the lower part. And then after that, this is called truncated CDF. Truncated CDF shows perfect exponential distribution. So point is, exponential distribution is pretty common, not only for United States, but say for United Kingdom. And now my last slide. This is very busy graph for 67 countries around the world. This is European countries, and this is other countries in the world. They're all shown in log linear scale. And you see basically for pretty much all of those countries, the middle part of the distribution, you pick any country you like, follows exponential distribution. There are deviations, of course, at the high end because there is upper tail, but these are not captured in this data because this data come from surveys, census and this kind of agencies, surveys of population. Surveys do not capture upper tail very well. And also in many countries, there are deviations at the low end. And these are because of, I suppose, that's my guess, because of social security policies. In many European countries, there are social security, welfare, social welfare policies, which reduce population at the low end, reduce poverty, etc. And so there will be deviation at the low end. So what is shown here is only the middle part of the distribution. It is the middle part that follows exponential pattern. Also, maybe for the other countries of the world, I want to emphasize China. See, in China, again, it follows very, very nice exponential distribution of a pretty wide range, up to about 5 times the average income, etc. So anyway, so bottom line, I would say we found, I would argue for universality of this exponential pattern of income distribution for the majority of population, the middle part, combined with power law distribution at the high end, and also maybe reduced distribution at the low end if there are social policies, which may or may not be the case. Okay, so I think I basically run out of my time, leaving some time for questions. Let me show you conclusions. I have, of course, many more slides, but let me show conclusions, and thank you, and we'll take a few questions. Thank you.
Okay, thank you very much. I didn't find any questions in the chat, so I will leave space to anyone in the audience. I don't see any hands raised, so if anyone has questions, just please start talking, maybe camera on.
I have a question on this distribution, on this changes of the income. There was also, I also saw that there was a change of the income of the poor part or poorest part of the population. And
this graph, right?
Yes, these are, and it's also like, these peaks are also at the same times as when the other class is also having an increase of the income. But still you have more people. But still you have more inequality. So why do you have more inequality anyway?
Yeah, let me comment this. Yes, very good point. So let's focus on these two graphs. So let me describe this blue graph is average income of lower class.
Again, I cannot.
Yeah, I think we're back to robot voice.
Okay, how about now? You sound good?
Yes.
Okay, good. Sorry, okay. So when I try to do anyway, it's a computer problem. So here is the deal. Yes. So the story is that during this bubble, the income of the upper class was increasing. The income of the lower class was increasing too. So during the bubble, during the boom in the market, everybody go up. The different point is that the upper class goes up much faster than lower class. So that's what raises inequality. So Gini coefficient increases. So you see, that's one of some kind of deceptive thing, because everybody's money go up. Everybody's happy, think it's great. But what people do not realize, that upper class growing much faster than lower class, okay, during this bubble. And that we can see only by quantitative analysis, by comparison, You see this is not just income of total amount of money going to the upper class. It's income of proportion going to upper class, you see? Okay, and then what happens during the recession? During the recession, something dramatic happens. The upper class shrinks. They actually lose money on stock market, whereas lower class income stays flat. So during recession, the upper class stays flat. No raises, everything is frozen. No raise, no. But real economy has to go on. Again, next bubble. Upper class share goes up tremendously. Lower class goes up again. Income of the upper class increases, and then during the crash, upper class shrinks. They lose money on this, real estate market, but lower class stays more or less flat, maybe slightly decreasing, but more or less flat. So that's how it works. So during recessions, lower class stays more or less flat, no increase. Yes, but during bubbles, upper class gains a lot more. And now, of course, we have this. Well, anyway, so this quantitative reasons, the injection of money. Injection of money indeed produced increase of overall, economic growth in the United States. So, to some degree, in some sense, the mission was accomplished by injection of money. But the problem is, it seems to be a very inefficient way of doing this, because the amount of money of the upper class during the injection of money by central bank increased a lot more than lower class. So injecting money, yes, does stimulate economy, but but stimulates upper class a lot more than lower class.
Thank you.
Okay, thank you very much. It seems we are right on time for the next presentation. So thank you for the talk. And now I will invite the second speaker, who is Michał Chorowski, in the presentation on market competition and government interventionism, a Monte Carlo approach. This will be the standard presentation, so around 12 minutes for the presentation itself, and then a few minutes for questions. So the floor is yours.
Yes, I prepared the video to be sure I fit in the time. Can you hear me?
Yes.
All right. Hello, my name is Michał Chorowski, and I'm a PhD student at the Faculty of Physics at the University of Warsaw. And today I would like to present to you a project I've been working on together with my advisor, Professor Ryszard Kutner. The project is about market competition and government interventions. The goal of our work is to propose and study a significant extension of a numerical model of economic growth inspired by a non-equilibrium statistical physics on a lattice. We consider the government intervention in the company market. We compare the predictions of our model with empirical data in order to find the connection between the government interventionism and the economic growth. First, we simulate a market of some country as a two-dimensional lattice of firms. As you can see on the left, the firms occupy nodes in the lattice, and the empty sites mean that other firms can move into those locations or that new firms can be created here. Each firm is described by two numbers, its technology level AI and the percentage market shares omega I. When we average the technology of all firms using shares as weights, we obtain the market technology level, which can later be used to describe the technological level of different countries. Lastly, we assume that there exists some world technological frontier, for example, the United States, whose technology grows exponentially with some parameter sigma, for example, 1%. The algorithm uses a Monte Carlo method at two time scales: the micro scale of individual firms and the global scale of the entire market. It goes as follows. We pick a random firm I out of n firms, and we calculate its survival probability T. The formula for the survival is separated into two cases. When the average technology is below 1, which applies to countries at earlier stages of development, and when it is greater or equal to 1 at later stages of development. The survival probability depends on the difference between the frontier and the firm's technology and parameter S, which describes the susceptibility to technological backwardness. Parameter S can also be understood as the level of competitiveness in the market, since higher S puts a higher pressure on firms to innovate, as they're more likely to bankrupt if their technology is low. In the early stages of development, the exponential growth of the frontier in this formula is slightly damped by the average technology level, which gives companies a greater chance to survive. Next, we pick a random number, R, between 0 and 1 from a uniform distribution, and if it's greater than P, the firm bankrupts. Otherwise, the firm moves to a random neighboring location. If the chosen site was occupied or there exists a neighbor at the new location, the firms interact and they create a spin-off with probability B or merge with probability 1 minus B. If there are no neighbors at the new location, the firm copies the technology of the world frontier, and the firm's technology is increased by R times the difference between the frontier and the firm's technology. Lastly, the algorithm goes back to point 1 until n firms has been chosen. Then a new Monte Carlo stepper site indicates. We tested several variations of government interventionism. We present here one of the possible options, the egalitarian approach. Again, we start with picking a random firm I out of n firms, but now the government gets a chance to intervene with probability Q. So with probability Q, the picked firm increases its technology by eta times R, which is a random number between 0 and 1, and the difference between the frontier and the firm's technology. And after this, the Monte Carlo step ends, which means that the next firm is picked. Parameter eta describes the effectiveness of the government intervention. High eta means that the government increases the technology of firms. Low eta means that the intervention's purpose is mostly just preserving the existence of firms without upgrading their technology. Since the intervention happens only with probability Q, if the intervention does not occur, the algorithm goes back to point 3 and continues normally. Now let's take a look at the results. Let's first look at the first row, which is the free market. The red lines are results averaged over 400 simulations, and the black lines are trajectories from single simulations. Here, as an example, we use the 10 by 10 lattice. The first plot shows the number of firms in the system in time. We see that the number of firms eventually decreases to a minimum possible number, which we chose as the 10% of the lattice size. The second plot shows the average technology level of the market, which grows exponentially. And the third plot shows the average technology to frontier ratio. We see that in the free market, the average technology gets very close to the frontier, around 200 steps, and stays there very close. When we set the probability and effectiveness of intervention to 50%, we see that the firms indeed disappear slower as expected, and the average technology is similar to the one in the free market. Moreover, such economy under intervention catches up to the frontier even faster. Lastly, we show what happens when there is very high probability of intervention, but the effectiveness is 0. In this case, it takes much longer for firms to disappear, but the average technology after 500 steps is only 25, so almost 6 times lower than in the free market. Also, the single trajectories show that the growth becomes very unstable. This is confirmed by the last plot, which shows that the country under such government might never catch up to the world frontier. Next, we studied how intervention affects the technology in the long run. The horizontal axis is the intervention probability, the vertical axis is the intervention effectiveness, and color is the average technology to frontier ratio in the long run. In this case, after about 500 steps. So plateau equal to 1 would correspond to frontiers technology. 0.00 on the plot is the free market. We see that a high effectiveness and high probability can bring a market very close to the world frontier, but a high probability and low effectiveness can even lead to a market collapse. From this plot, we can say that when it comes to government policies, quality is usually better than quantity, because using eta is helpful, or at worst, makes no impact on the technology in the long run, but using Q can sometimes be quite dangerous. Now we wanted to see how the results change as S, the susceptibility to technological backwardness, changes. This axis shows the probability of the intervention. This is the efficiency eta, and the vertical axis is the technology growth over 40 steps, which we can later interpret as, for example, 40 years. We see that as in the heat map before, for Q equal to 1 and eta equal to 0, the technology growth is close to 0. However, when the market is highly competitive, as the green surface, there is not much benefit to any kind of intervention, even when it has high quality. At the same time, countries which are less developed, for example with S equal to 2% as the pink surface, a high quality of intervention might be extremely helpful to catch up to some more developed countries. In other words, the government interventionism might be more beneficial for less advanced and less competitive countries. The main takeaway from this part is that there is no one-size-fits-all intervention policy. The same kind of intervention policy in one market can lead to economic growth, but in a highly competitive market, it can be useless.
Therefore, the policy should always be fine-tuned for the specific character of the market. Next, we fitted the model to the empirical technology data for 28 OECD countries in the years 1960-1999. The empirical technology was extracted using a standard Cobb-Douglas function shown here, where Y is the GDP per capita in the 1990 USD, K is the physical capital per capita, and based on previous literature, we chose alpha equal to 0.315. Then A of T is the residual, which we use as an approximation for a country's technological level. Here we show some example fits of our model. In black is the empirical data extracted from the Cobb-Douglas function, and red is the fitted average technology level from our model. The fitted parameters were Q, eta, and S. We see that for the most part, the model fits the data quite well. However, not in all cases. For example, for Hungary, the fit could certainly be better. It has to be said that fitting this model is a challenge, since there can be different empirical measures of technology, and sometimes there is more than one combination of parameters that will give the same fit. So this is still a work in progress. Next, we wanted to build a bridge and find a connection between our theoretical parameters Q, S, and eta and the empirical economic growth. After we fitted our model to all 28 countries, we had the estimated parameters Q, S, and eta for each country. We also had the GDP per capita growth over almost 40 years for those countries. So we built a regression model that tried to explain the economic growth over those 40 years using those parameters. The formula is shown here, and we see that this model explains 67% of variance of the GDP growth. So I think this is quite okay. The regression passed all critical tests. The errors were homoscedastic and had a normal distribution. To sum up, the proposed extensions allowed us to model the government intervention in the market. We were able to specify the conditions in which the interventionism can be beneficial or destructive for the market. The fact that the interventionism lead to economic growth only in some conditions is consistent with other models. Our results also agree with other agent-based models, where it was found that the policies favoring innovation can promote faster GDP growth in both short and long run. The model parameters describing the intervention are tied to the empirical economic growth. The model is flexible and can be easily extended, for example, by introducing taxes that would finance the intervention.
All right, thank you very much. That was a good trick with the time, and we see that there's, even though we're zooming for a year now, all of us, there is always something to learn with the sound and stuff. So, are there any questions? If there are no questions, I will probably ask. So the regression that you show at the almost the end. I'm just wondering, because when you show this kind of a regression, I'm not gonna question the statistics around, because with 28 observations, that's always a bit problematic to have any reasonable fits. But can you make some kind of interpretation, or whether the parameters actually show what you would expect for this kind of a model? Or because, you know, just saying that it's 60% of variability is being explained, that's fine, but does it meet what you expected from the model? I mean, interpretation wise, or the direction of the effects wise, or stuff like that.
Well, the interpretation is not clear, because there are interaction terms involved as well. So that really depends on on other variables too. I think for the most part, it was according to my intuition, but it did give some unintuitive results for certain values of S, where the intervention would lead to some enormous decrease in the GDP over 40 years, which I think is it was a little too much. So This is certainly still something that we're working on.
Okay, thank you. Any other questions?
I have a question. I'm interested in these government interventions. Did you see some line or border where when government interventions stop being useful for the underdeveloped economies?
I did not look for a specific border, but certainly with higher S, so higher competitiveness in the market, it becomes less efficient.
Thank you.
All right, thank you very much. Any other questions? Maybe one short one? No? Okay, if not, then thank you very much again. Say hello to Ryszard for me. And we will move to the last presentation. The last presenter is Suzana Blesic, and the presentation on Hurst exponent, or sorry, Hurst Space Analysis data clustering technique for long-range correlated time series. So the floor is, or the screen is yours.
Thank you. Okay, I have also recorded my presentation. Oh, host disabled participant screen sharing. It says that I cannot share screen. Do you hear me?
Yeah, I hear you. I'm not sure if I'm in charge of these technical things. You're a co-host now, so you should be able to do it now.
Okay. All right. Share computer sound. Okay. So, okay. So today I'm going to talk about the Hurst Space Analysis, which is a technique that we developed in order to try to classify or cluster long-range time series from different complex systems. This technique, as we developed it, specifically looks into the cycles in LTP data. And here LTP stands for long-term persistent. And only by looking into the cycles and how the cycles in data behave, it quantifies records and then classifies it. Namely, if you're doing scaling analysis of any type in any type of complex system, and here I'm showing a DFA function of a spontaneous activity of a nerve cell, because nervous system was the first complex system that we were working in. What is visible in this real world data is that scaling functions are very rarely ideally linear functions on log-log graphs. That is, there are power law functions as theoretically they should be, but there are curves and bends in those functions where they deviate from, locally deviate from the linear behavior. And this can be for a number of reasons. One is the different dominance of noises when we have crossovers, but also like these slight bands, local bands, can be from cycles of different types. So from the very beginning, we started doing DFA together with wavelet spectrum analysis. And from the wavelet spectrum, this is the wavelet spectrum for the same record as shown before. So from the wavelet spectrum, we can see these cycles better. Like, for example, in the nerve cell activity, the cycles come from heart rate and from breathing, and then very dominantly from metabolic activity. And this is what we saw like when we started working on scaling analysis. But then, I mean, when we were working in neurosciences, this is something that we saw and discussed about, but really didn't go into detail then. Then we started working with financial data, and when we were analyzing data sets of stock market indices, again, we saw cycles in our wavelet spectra. But this time something else happened. We observed that when the cycles occur, when the cycles are occurring in our data, from our data set, they're always occurring at the same position, so at the same times. And these peak positions completely made sense for the human-induced behavior as the stock market, because they're like, this is in days, so they're like position 5 days, which is a working week, and then 7 days a week, and then 2 weeks, 3 weeks, a month, 3 months, 4 months, a year, and then there's also a cycle at 2 years. So then we said, like, okay, so it's not just that we are again seeing these cycles, and this is something that we were already thinking about, but there is something universal about their appearance. So we decided to, work on them more and look more to like concentrate more in detail about and try to figure out or understand what is happening. So what we did first, we went through the literature and then found from Blesic and Stefanowska. They were analyzing wavelet spectra from the human blood flow dynamics, and what they did, they find the same thing in the wavelet spectra of the human blood flow dynamics. So first they saw that they have peaks in wavelet spectra, and then they saw that they're appearing at the same positions. So they decided to treat them as one would treat peaks in the Fourier spectra. So they calculated several things. They quantified them by calculating their amplitudes and also their energy. So they integrated under the peaks. And then they compared these values for different groups of people. And for example, in their paper, they showed that they saw difference in these values in a group of people with heart disease, and then in a group of healthy controls. So we decided to try to do the same thing with our market data. We chose a data set of time series of stock market indices, and we chose them so that they have indices from markets from underdeveloped markets, and then from emerging markets, and then from developed markets. And then we identified 9 peaks that were universal throughout this data set. And then we calculated these values the same as Blesic and Stefanowska, the amplitude and energy under the peaks. And we got the results. We got some kind of relation between developed and underdeveloped markets, but then these results were not really satisfying to us. They were not very elegant, and they were also not very straightforward. So we decided to work on that some more. So this is how we developed the Hurst Space Analysis. So what we did first, we went back to the scaling analysis, the thing that we do. So we calculated the local Hurst exponents or scaling exponents for the all our time series TS in our dataset under the selected peaks. For that, we used time-dependent the trended moving average analysis, that is centered trended moving average analysis, because this analysis is very good for scanning throughout, locally scanning throughout the time series. So we represented each time series with a vector, Hurst vector H, that continues scaling exponents under each peak that is identified for the whole complex system, so the universal peak for that time series as the element. Then we defined the mean value for the whole series of these H vectors that define what we call Hurst space, and then we defined unit vectors S for every vector H that are differences between vectors H and mean vectors M. We were hoping that in this way, by defining S in this way, we will have this classification and differentiation of vectors by the value of S and also by their sign. And we did get some, but again, like we differentiated developed and underdeveloped markets, but not very good the emergent markets. So then we decided to add another step to our Hurst Space Analysis procedure. We decided not to look at the mean value as a reference value, but to define some preferred direction or preferred kind of behavior that we actually want to look at, and then compare everything to that kind of behavior. So we define the vector, unit vector of this preferred direction, and for the finance data, we define it this way. And in this way, we, by this definition, we actually preferred behavior of the developed markets over behavior of the underdeveloped markets. So graphically, it will look like this. This is our direction E, and then this is pointing towards developed markets. And then by projecting all our vectors to this preferred direction, we got this differentiation between underdeveloped markets, emerging markets, and developed markets. And it looked like this. So this is our result for the markets. And although it looks trivial because, I mean, this is the differentiation of the markets. Anyway, this is the differentiation done only by calculating the characteristic of the cycles in wavelet spectra. So now we have used analysis for the climate data, and I will just show you quickly. So this is the DFA function and wavelet spectrum for the time series of global temperature data. And they show wavelet spectrum shows 4 peaks in the time period up to 1 decade, which is a statistically significant period for the amount of data that we have. So these were our peaks that we have chosen for Hurst Space. And then we defined the preferred direction in this way. So our preferred direction was pointing away from the oceans. So going to the global temperature data or more continental data. And then this is the result that we got. We got clear differentiation of the oceans, and then mountains and plains, and then Arctic deserts. And moreover, in this case, we came back and looked into wavelet spectra of this cluster data, and in this we have 4 clusters in the climate data, and we can see from the wavelet spectra which are the peaks that are dominating behavior of these 4 types of behavior. So oceanic, and then 2 types of continental, and then Arctic and desert data. And so this can be further used to try to identify the influences on the climate of these particular regions.
Okay, thank you very much for the presentation. I'll just check the chat whether there are questions. I don't see anything there, but I got disconnected for a few seconds, so maybe it erased. So if anyone has questions, now is the time. Okay, I see no hands raised in the list. I see no questions in the chat. I don't have a question either. I'm I'm sorry.
No, it's absolutely okay.
Yeah. Okay. So if there are no questions, then thank you very much to all 3 presenters. and enjoy the rest of the conference, and we'll see each other around probably in some other sessions. So enjoy the rest of your evening, or depending where you are, and see you around. Bye.